Hello everyone, section 12.5, permutations and combinations. Example 1's been done for you already. A coin is tossed and die is rolled. Find the number of outcomes and sequence of events. That is multiplication of choices, 2 times 6 or 12. We found the same result back in section 12.1 when we wrote out a sample space and counted the answers. Example 2. Consider the permutations of the letters in the word pencils. So there are 7 letters, so multiplication of choices, 7 times 6 times 5 times 4 times 3 times 2 times 1 gives us 5,030 choices. How many ways can you arrange 3 of the letters? That's 7 times 6 times 5, so we only have 3 of the letters, which is 210 possibilities. So here we want to get some practice with factorials. This is a very handy tool that we're going to need. So 8 factorial. We use our factorial key on our calculator, which is this exclamation point. Every scientific calculator has one. So you're going to have to find it on yours where you have the exclamation point. Typically it's a button. Some calculators you have to go to a probability section or a math section, math key or math key or a probability key on your calculator to find where the factorial function is. So 8 factorial is 40,320. 10 factorial is 3,628,800. Now this is going to look weird and you're going to be confused. You're probably going to assume that this is 0, but it's not. And if you do it in your calculator, 0 factorial is actually 1. That becomes important to us later on when we're doing a problem like 4p4 and things like that. We may have 0 factorials that we have to have the value of 1 for. 1 factorial also is 1. If you check that on your calculator, you'll get 1. 6 factorial, 720. 11 factorial. These numbers get huge really fast. Factorial is a really fast climbing function. 39,916,800 is 11 factorial. 2 factorial is 2. 2 times 1, 2. 9 factorial, 300. 362,880. Now, the reason that I have problems I and J here are to show us that we don't need to use our calculators right away on these. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, 7 times 6 times 5 times 4 times 3 times 2 times 1 cancels with the 7 times 6 times 5 times 4 times 3 times 2 times 1 on the numerator. So we have 10 times 9 times 8 left. 9 times 8 is 72, times 10 is 720. So again, you can do that on your calculator. So if we do 10 factorial divided by 7 factorial, we do get 720, which is the same answer as we got a second ago. But sometimes, and there are factorials that our calculators can't do. For example, if I try to do 100 factorial, this calculator will do 100 factorial, but it won't do 150 factorial. Most of your calculators won't go over 69 factorial. They won't do a 70 factorial. So once you get a number that is too big to even do in your calculator, you have to find some way to cancel things so that we can get down to a number that our calculators can do. If we take a look at this one, this is 10 factorial divided by 8 factorial, which is 10 times 9, or 90, after you do the reducing. Okay? And again, this becomes very useful when we start doing permutations. As we can see, the permutation formula is n factorial, so NPR, n items chosen r different ways in permutation, is n factorial divided by n minus r factorial. So we get situations like these quite often. So let's take a look at these problems. 7 factorial over 7 minus 5 factorial, or 7 factorial over 2 factorial, or 7 factorial divided by 2. Factorial divided by 2 is 2,520. 12p4 is 12 factorial over 8 factorial. 12 factorial divided by 8 factorial. So we get 20,100. 12 factorial divided by 8 factorial. Sorry, I must have hit a button incorrectly in my calculator. 11,880. 5p3, 5 factorial over 2 factorial. 5 factorial divided by 2 is 60. 6 factorial over 6 minus 0 factorial is 6 factorial over 6 factorial, which is 1. So 6 items chosen 0 ways. There's one way to do that. Alright, 5 factorial, 5p5 is 5 factorial over 5 minus 5 factorial. 5 factorial over 0 factorial. And this is where this comes into play from earlier, where we have to remember that 0 factorial is 1. So 5 factorial divided by 1 is 5 factorial, which is 120. Okay, 6p2, 6 factorial over 4 factorial is 6 times 5, or 30. Sometimes they're nice and easy and you can do them right in your head. 9 factorial over 6 factorial, divided by 6 factorial. 9 factorial divided by 6 factorial. Divided by 3 factorial. Sorry. See what happens when you start doing them too quickly? 9 factorial divided by 3 factorial divided by 6 is 60,480. Okay. 11p4. It's 11 factorial over 7 factorial. 11 factorial divided by 7 factorial. 7,920. 8p0. I'm not even going to write it out. It's going to be exactly the same as 6p0, 6 factorial over 6 minus 0 factorial, or 8 factorial over 8 minus 0 factorial, 8 factorial over 8 factorial. 1. 10p2, 10 factorial over 8 factorial, which is 10 times 9, or 90, which is the same one that we got up here. So j up here is the same as j down here. Okay. Question number 5. 8 people serve on a committee. How many different ways can a chairperson, a recorder, and a treasurer be chosen from the committee members? So this is, there are 8 members. We're doing choosing 3 of them. And let me clarify, order matters here, because we have one of them is going to be a chairperson, another one's going to be a recorder, and another one's going to be a treasurer. So these 3 people matter because they have 3 different positions. So order matters here. And that becomes important when we start doing combinations. These are permutations, hence the P. Order matters. Remember that. So 8 factorial over 5 factorial, or 8 times 7 times 6, or 336 possible permutations for choosing chairman, a recorder, and a treasurer. Okay, example 6. Drea and Brian are auditioning for a part in the school play. There are 15 people auditioning. The order of their auditions is chosen at random. Find the probability that Drea auditions last and Brian auditions second to last. So there are 15 people in the play. So how many different ways can we choose 15 people if order matters? 15 P15 is equal to 15 factorial, which we saw right here when we did 5p5. 5p5 is 5 factorial of 0 factorial, or 5 factorial. So here we have 15 factorial, which is a big number. 15 factorial is gigantic. I'm not even going to write it all out. It's got 13 digits in it. That's our denominator because we're finding probability. That's how many possible ways there are to choose the 15 people. We want the favorable outcomes. The favorable outcomes is where we have 13 of them chosen before we choose Drea and Brian. So that's 13 factorial over 15 factorial, which is 1 over 15 times 14, or 1 over 210. So 1 out of 210 possibilities will have Drea last and Brian second to last. Example 7. A combination lock consists of 26 letters of the alphabet. If a 3-letter combination is needed, find the probability that the combination will consist of the number of the letters A, B, C in that order. The same letter can be used more than once. We could have AAA or BBB or XXX. Note, combination lock is poorly named. It really should be called a permutation lock, because with a lock, order matters. So it really should be called a permutation lock. Somebody called it a combination lock a long time ago, and the name just kind of stuck. So how do we do this one? Well, for the first letter there are 26 choices. For the second letter, there are 26 choices because we can repeat. And for the third letter, there are 26 choices. That's 26 cubed. One of those combinations is A, B, C. There's only one way you get A, B, C. So 1 out of 26 cubed combinations, or 1 out of 17,576 is our probability that we get A, B, C as a combination on the lock. All right, now that we mentioned combinations, order does not matter. That's why a lock, combination lock, is not a combination lock. It's a permutation lock, because the word combinations in math means the order doesn't matter. In other words, there's no difference between AB and BA or CA and AC. So if this is our sample space, we can cross off all these ones because this is the same as this one, this is the same as this one, this is the same as this one, so on and so forth. So in permutations, if we had two-letter combinations of A, B, C, and D, there would be 12 possibilities. But in combinations, if the order didn't actually matter, then there's only 6 possibilities. Okay? We have a formula for figuring out combinations. It's similar to the permutations formula, but it adds in this r factorial in the denominator that wasn't in the permutations formula. Okay. So let's get some practice doing combinations and using the formula. So we have 5 choose 2 is 5 factorial over 3 factorial 2 factorial, which is, if you do this on your calculator, 10. 8 factorial over 5 factorial 3 factorial, which is equal to 56. 7C4 is 7 factorial over 3 factorial 4 factorial, and this becomes, do this out on our calculator, 35. For D, 6 choose 2, 6 factorial over 4 factorial 2 factorial. This one's equal to 15. Again, this is just good practice with your calculators and with the formula. 6 factorial over 2 factorial 4 factorial gives us 15 again. With permutations, when we did 3P0, this is going to be 3C0. This is 3 factorial over 3 factorial 0 factorial, remembering that 0 factorial is 1. So this is really 3 factorial over 3 factorial, which is 1. 3C3, 3 factorial over 0 factorial 3 factorial, and again, we get 1. 9 factorial over 2 factorial 7 factorial. This one gives us 36. 12 factorial over 10 factorial 2 factorial gives us 66. 4 factorial over 1 factorial 3 factorial is 4. That's example 8. Example 9, you're listening to music and you have time to hear only 3 songs from your playlist of 16 songs. How many combinations of 3 songs are possible? So we have 16 songs. We're choosing 3 of them. Order doesn't matter. The order of the 3 songs doesn't matter. You just have time to listen to 3 songs. So this is 16 factorial over 13 factorial 3 factorial, which gives us 560 possible combinations. Example 10. The art teacher has selected 13 projects, including one of yours and one of your friends to use in the display case in the hallway. Projects are placed at random. There is room for 2 projects in the middle row of each case. What is the probability that your project and your friend's project are placed in the middle row? So, there are 13 projects. We're choosing 2 of them. That's 13 factorial over 11 factorial 2 factorial, or 78 possible combinations. That's our denominator. One of those combinations has you and your friend's projects side by side. So 1 out of 78 chance that you and your friend's projects are right next to each other. How many different 4-letter permutations can be formed from the letters in the word decagon? 1, 2, 3, 4, 5, 6, 7 letters. 7p4 is 7 factorial over 3 factorial, or 840 permutations. All right. ID cards. How many different cards can be made if there are 6 digits on a card and no digit can be used more than once? So order matters, and we're not replacing any of them. So 10 P6 is equal to 10 factorial over 4 factorial, which is equal to 151,200 possible permutations. Okay, and again, I chose P here because order mattered. Textbook selection. How many different ways can a teacher select 2 textbooks from a possible 17? Again, ask yourself, does order matter? No. The order of the textbooks is irrelevant, or at least it doesn't say that it's relevant. So this is 17C2, or 17 factorial over 15 factorial 2 factorial, or 136 possible combinations. Okay, poker hands. Royal flush. A royal flush is ace, king, queen, jack, 10, all of the same suit. So I have hearts royal flush shown here. How many of these are there? Well, there's the hearts royal flush, clubs, diamonds, and spades. There are 4 possible royal flushes. Straight flush. How many straight flushes are there? Well, a straight flush is ace, 2, 3, 4, 5, all of the same suit, or 2, 3, 4, 5, 6, all of the same suit, 3, 4, 5, 6, 7, all of the same suit, all the way down to 10, jack, queen, king, ace, all of the same suit. So how many of these are there? Well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them, times the 4 different suits, because this is, say, all the hearts flushes, and then we've got all the clubs, diamonds, spades, flushes. So there are 10 times the 4 suits is equal to 40, but we're not including the 4 royal flushes, so we're subtracting 4 of them. So I didn't even need to count these. So I could have done 9 times 4 here. Either I do 10 times 4 and then subtract 4, or I do 9 times 4 and don't subtract 4 because I subtracted in the beginning. Either way, there are 36 straight flushes. in a 5-card poker hand. All right, 4 of a kinds. So how many 4 of a kinds are there? Well, you can get ace, 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 and then a 5th card, which we don't know. All I know, it's not an ace. I can get 2, 2, 2, 2, and a 5th card that we don't know what it is. All the way down to queen, 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 and a 5th card, king, 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 and a 5th card. So how many of these are there? There are 13 of these. And how many of the 5th cards are there? Well, there are 52 cards in the deck. 4 of them have already been chosen. So there are 48 cards left for that 5th card possibility. When you multiply these together, you get 624 possible 4 of a kind hands. All right, full houses. How many different full houses are there? So what is a full house? A full house is 3 matching cards, 10, 10, 10, and 2 matching cards, a pair. So 3 of a kind and 2 of a kind, a pair. King, king. So how is this? So in other words, it could be, there are 4 tens, I'll use this one as our example, and we're choosing 3 of them, times there are 4 kings, and we're choosing 2 of them. Order doesn't matter, whether you dealt the king of clubs first and then the king of hearts, or the king of hearts and then the king of clubs. That order doesn't matter. So that's why we're choosing combinations here. Okay. So what is this? This is 4 factorial over 3 factorial, sorry, 1 factorial, 3 factorial. 1 factorial, 3 factorial, times 4 factorial over 2 factorial, 2 factorial. This is 4. Times, this gives me, if I reduce here and here, this is going to give me 3 times 2, or 24 possible ways of getting the kings with the tens. Well, I didn't have to get kings and tens over kings. I could have gotten queens over jacks, or 5s over 7s. There's 13 possible 3 of a kinds. And then once I've chosen my 3 of a kinds, there's only 12 possible 2 of a kinds, because I've already chosen one of the 3 of a kinds. And when I multiply this, I get 3,744 possible full house combinations. Okay. Find the probability of getting 4 aces when 5 cards are drawn from an ordinary deck of cards. So there are how many possible ways of getting 5 cards? Well, there are 52 cards in the deck. We're choosing 5 of them. And when we do this out, that is a large number. In fact, let's write it. 2,548,960 possible 5-card hands. Okay. See if that focuses a little bit better. A little bit. All right. There's one way to get 4 aces. 4, choose 4 is 1. But then there are 48 5th cards left, times 48 5th cards, right? We found this when we were looking at on the back side here. When we were looking at 4 of a kinds here, that there were 48 possible fifth cards to go along with our 4 aces. Okay, so in this case it would be 1 times 48 instead of 13 times 48 because we're only looking at the 4 aces. So this is now 48 out of 2,548,960, or 1 out of 54,145 different 5-card hands is going to be 4 aces. All right, example 16. Part A, defective transistors. A box containing 24 transistors, 4 of which are defective. If 4 are sold at random, find the following probabilities. We want to find the probability that exactly 2 of them are defective. So how many possible ways, total ways, can we sell these transistors? Well, there are 24 of them. Choosing 4 of them. And that gives me 10,626 possible combinations for the 24 transistors to be sold, 4 of them. And we want 2 of them to be defective. So there are 4 defective ones. We're choosing 2 of them. That's 4, choose 2. That's 12. And if I'm choosing, taking out 2 of the 4 defective ones, then the other 2 are going to be not defective. They're going to be fine. So there are 20 that are perfectly fine, and we're choosing 2 of those. So 20, choose 2. Factorial, divided by 18, factorial, divided by 2, 190. So we now have, for our probability, 4, choose 2, times 20, choose 2, over the total possible, 24, choose 4, is 1140 over 10, 626, or 190 out of 1771. Sorry, this 4 choose 2 is actually 6, not 12. Shouldn't have tried to do it in my head that quickly. So 190 divided by 1771 is approximately 10.7%. So there's a 10.7% chance that 2 of the 4 transistors are defective. What's the probability that none of them are defective? So I'm sorry, this up here, this is probability of exactly 2 defective. All right, probability no defective. So there are 20 non-defectives. We're choosing 4 of them. Out of the 24, choose 4 possibilities altogether. And that's 4,845 out of the 10,626 possible. 1615 over 3542, or approximately 45.6% chance that none of them are defective. Probability that all of them are defective. So there's one way, there are only 4 defectives, so there's only one way to get all 4 of them to be defective out of the 10,626 possibilities, or approximately 0.00941% chance. All right. At least one is defective. Probability, at least one defective. So, like we've mentioned many times before, the second we see at least, we trigger the complement rule. So 1 minus probability that no defectives is equal to 1 minus no defectives was 1,615 over 3,542, which is 1927 over 3,542, or approximately 54.4% chance, which makes sense. So if I add that to the 45.6%, I have 100%. Okay. Example 17. A store has 6 TV graphic magazines and 8 Newstime magazines on the counter. If 2 customers purchase a magazine, find the probability that one of each magazine was purchased. So we have 6 TV graphic magazines, choosing one of them, times 8 Newstime magazines, choosing one of them, divided by there are 14 total magazines, and we're choosing 2 of them. When we do this out, this is 6 times 8, which we know from our exercises. 6C1 is 6, 8C1 is 8, divided by 14C2 is 91. 48 out of 91, or approximately 52.75%. Okay. Example 18. State lottery winners. In Pennsylvania state lottery, a person selects a 3-digit number. Digits are 0 through 9, and repetitions are permitted. So 0, 0, 0 is a possibility. 1, 1, 1 is a possibility. All the way down to 9, 9, 9 is a possibility. So that's a total of 1,000 possibilities. Well, if a winning number is selected, find the probability that we'll have all 3 digits the same. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 of them where all 3 digits are exactly the same. So 10 out of 1,000, or 1 in 100, or 1% chance that all 3 digits will be the same. Tennis tournament. There are 8 married couples in a tennis tournament, in a tennis club. If one man and one woman are selected at random to play in the summer tournament, find the probability that they are married to each other. Since there are 8 ways to select a man, and there are 8 ways to select a woman, and there are 8 times 8, or 64 possible ways of choosing one man and one woman. All right, so that's our total in the denominator. Since there are 8 married couples, there are 8 out of the 64 possibilities would be married, or 1/8, or approximately 12.5%. Senate partisanship. The composition of the Senate of the 104th Congress is 41 Republicans, 2 Independents, and 57 Democrats. A new committee is being formed to study the ways to benefit the arts and education. If 3 senators are selected at random to head the committee, what is the probability that they will all be Republicans? What's the probability they will all be Democrats? What's the probability there will be one from each party, including the Independents? So there are 100 senators, and if we're making a committee of 3, it's 100C3, or 100 factorial over 97 factorial 3 factorial, or 161,700 possible combinations for choosing the 3 senators. If we're going to do probability that all 3 are Republicans, then there are 41 Republicans. We're choosing 3 different ways out of the 161,700 total possibilities, which gives us 10,660 out of the 161,700, or approximately 6.59% chance that all 3 will be Republicans. What's the probability that all will be Democrats? All Democrats. So there are 57 Democrats. It's 57 choose 3 divided by the 161,700. That's equal to, this one didn't divide evenly. It's 29,259.9 repeating out of the 161,700, or approximately 18.1% chance that all 3 of them will be Democrats. Now, the tricky one is probability that we get one from each. There are 41 Democrats, 2 Independents, and 41 Republicans, 2 Independents, 57 Republicans, divided by the 161,700. And when we divide this out, we get approximately 2.9% chance that one is taking from each of the 3 parties. Okay. Example 21. Encyclopedia Britannica's list of 20 world-class orchestras include the following from the United States. I'm not going to read all the list, but there are 7 of them from the United States. We're choosing 5 at random from the list of 20 for a benefit CD. What is the probability that the selection will include at least 1 group from the United States, at least 2 from the United States, and that all 5 will be from the United States? So, again, when I see at least, I think complement rule, but let's start off by, there are 20 orchestras. We're choosing 5 of them. That's 20 factorial over 15 factorial 5 factorial, or 15,504 combinations of orchestras. Let's see if we can get that to focus again. Good. If we want at least one group from the United States, then that means, let's look at the reverse of that. None of the groups are from the United States. So there are 7 from the United States. That means that there are 13 not from the United States. So we have 13, choose all 5 from those 13 that aren't from the United States. So now we have 13 factorial over 8 factorial, 5 factorial, or 1,287 possible ways to choose nobody from the United States. Well, we want the probability of at least one. So that probability is the 15,504 minus the 1,287 possible. So we now have 14,217 out of the 15,504, which is approximately 91.7% chance that at least one is from the United States. At least 2 probability, at least 2. This is the tricky one. So we already have the at least 1. So this is all the non-United States combinations. Now, what if we also need to calculate the probability of there being 1 from the United States. So if there are 13 that aren't from the United States, and we choose 4 of them, and we multiply that times the 7 from the United States, where we're only choosing 1 of them. So this is 13 factorial over 9 factorial 4 factorial times 7. 7C1 is 7. And this is 5,005. So we already subtracted 1,287 from the 15,504, and we got this. If we subtract an additional 5,005 from this, we are now at 9,212 out of the 15,504, or approximately 59.4% chance that at least 2 are from the United States. Last one, probability of all 5 being from the United States. So this is, come over here, I got a little bit of space over here to the right. There are 7 in the United States. We're choosing 5 of them. So 7 factorial over 2 factorial, 5 factorial, which is exactly equal to 21. So we have 21 divided by 15,504, or approximately 0.14% chance that all 5 are from the United States. Thank you very much.